Okay, so in section 7.5, we are working on something called the sum and difference formulas. And if you've pulled up our class formula sheet, the first thing I want you to notice is that the sum and difference formulas are on the formula sheet. So you do not need to memorize these for the exam. So what I'm going to do is I'm going to write down 3 formulas. I'll give you guys a couple minutes to jot them down, and then we'll talk about the different formulas, and then we'll do a bunch of problems where we apply these. So the first one, we have sine of alpha plus or minus beta is equal to sine of alpha cosine beta plus or minus cosine alpha sine of beta. The second one, and I'll explain these as soon as we get them all down, is cosine of alpha plus or minus beta is equal to cosine of alpha cosine of beta minus or plus sine of alpha sine of beta. And then the third one here is tangent of alpha plus or minus beta is equal to tangent of alpha plus or minus tangent of beta all over 1 minus or plus tangent alpha tangent beta. Okay, so I'll give you guys some time to get those down, and then we'll talk about them. So I'm sure you have questions already. We'll answer them all in just a second here. Anybody in class want one of these formula sheets that didn't get one? Welcome to grab one. Okay, so let's talk about these 3 formulas. So the first thing is, normally in this class, I don't just like to give you a formula without a proof, right? Usually we work through the proofs together and then we come up with the formulas ourselves and put them in a box. But for these 3 formulas, the proofs are somewhat complicated. They're also somewhat long, and I don't think they give you an aha moment, like, oh, now I see exactly where those formulas come from. That was so simple. So on these ones, I'm going to skip the proof. If you're interested in viewing the proof, they're in the textbook, or you can Google proof of sum and difference formulas, and there's some pretty cool videos online. Okay, so first up, I'm going to skip the proofs. So second thing, let's talk about what these formulas are. These are formulas that allow us to find sine of the sum or difference of 2 different angles. So up to this point, for example, we only know how to evaluate a few angles by hand. So we could do sine, cosine, and tangent of multiples of 30, 60, 90, right? That's our first triangle. 45, 45, 90, that's our second triangle, and then those quadrantal angles. So now what it's going to allow us to do is find things like, say, sine of 15, right? 15 would be 45 minus 30. We can plug in angles we know how to do by hand and use these formulas to find sine, cosine, tangent of the sum and difference of angles we know how to do by hand. So this kind of expands what we can evaluate. Okay, so the next thing we want to talk about is that this is actually 6 formulas combined into 3. So the way these plus or minus operators work are different than that plus or minus that we typically see in front of a square root or in that quadratic formula. So this is different. So the first one, here we have the plus on top and the minus on bottom. And you can see over here we have a minus on top and a plus on the bottom. The way that these formulas work is that the operators that are on top go together. So our first formula says sine of alpha plus beta is equal to sine of alpha cosine beta plus cosine alpha sine of beta. The second formula says sine of alpha minus beta is equal to sine of alpha cosine beta minus cosine alpha sine of beta. So the bottom operators go together there. Okay, our next formula, the top operators go together. So the next formula, you see we have a plus on the left and a minus on the right. The top operators go together. Then our bottom operators go together. So these two go together. So the next formula would be cosine of alpha minus beta, cosine alpha, cosine beta plus sine of alpha, sine of beta. Okay, down here we have three operators. So the top operators all go together. And then the bottom operators all go together. Okay, so first formula would be tangent of alpha plus beta is equal to tangent of alpha plus tangent beta over 1 minus tangent of alpha tangent beta. And then the second one would be the operators on the bottom. Okay, so actually 6 formulas combined into 3. So what we'll do is we'll just jump right into some examples and we'll see how these work out. I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 examples for you in this section. The good thing about this section is I think I said this on the last couple too, is it's really nothing new. All we're doing is kind of using what we've already learned in the previous section and plugging it into a new formula. So first up, let's find the value of sine of 7 pi over 12. Okay, so the first thing you should notice is 7 pi over 12. That is not a multiple of 30, 60, 90, or 45, 45, 90, or pi over 3, pi over 4, pi over 6, pi over 2, right? Those are the ones we know how to do by hand. So what our goal is to write it as the sum or difference of 2 angles that we do know how to evaluate by hand. Now, there are an infinite number of ways to rewrite this. Okay, so I'm going to show you what I picked. And if other numbers pop into your head suddenly, that's fine too. There's an infinite number of ways to rewrite this as a sum or difference of angles that we know how to do by hand. Okay, so what I like to do, I'll do this in radians and then I'll also show it to you in degrees, and you're welcome to do it either way. So I'm going to write it as the sum or difference of 2 angles we know how to do by hand. Okay, so what I want to think about here when this is in terms of radians is this is 7/12. So I think about the number 7, and I want to think about what 2 numbers add to 7, and then do those fractions reduce to angles that we know how to do by hand. So of course, the first one for 7 would be 1 plus 6. So we could write this as 1 pi over 12 plus 6 pi over 12. The 1 pi over 12 wouldn't reduce to anything we know how to do by hand. The 6 pi over 12 would, but we need to get both of these to be angles we know how to do by hand. Okay, the next option would be 2 plus 5, right? I'm trying to add up to the 7, so 2 plus 5. So I have 2 12ths and 5 12ths. The 2 12ths would reduce nicely, but the 5 12ths wouldn't. Okay, so the next way we can add up to 7 would be 3 plus 4. Okay, so it turns out here, if I write this as 3 pi over 12 plus 4 pi over 12, these angles both reduce to angles we know how to do by hand. So let's take a look. 3 pi over 12 reduces to pi over 4, and 4 pi over 12 reduces to pi over 3. The goal is to get this as the sum or difference of 2 angles that we can evaluate by hand. Okay, so the other way of doing this is right off the bat, converting to degrees. So 7 pi over 12 happens to be 105 degrees. So if you wanted to look at it this way, we think about how can we write it as the sum of angles we know how to do by hand, and that would be 45 plus 60. Okay, again, this is only one way of doing it. There's an infinite number of ways of doing this as a sum or difference. If you want to do this in degrees, that's totally fine. This is not your final answer. These are just the middle steps. So if you like that better, be my guest. All right, so what we want to do is we have sine of something plus something. So this is going to be the sum formula. This I'm going to call angle alpha, and this I'm going to call angle beta. If we look up here, I have sine of alpha plus beta. That's going to be equal to sine of alpha cosine beta plus cosine alpha sine of beta. So all I'm going to do is use this formula and fill in alpha and beta. Alpha is going to be pi over 4 or 45 degrees if you like degrees better. Beta is going to be pi over 3 or 60 degrees if you like that better. So using my formula, I get sine of alpha, which is pi over 4, times cosine of beta, which is pi over 3. Since we have the plus here, that's the top operator. We need to use this top operator. So we have cosine alpha, which is pi over 4, times sine of beta, which is pi over 3. Okay, our next step is to fill in these values and then simplify as much as possible. And I find that in this section, one of the challenges is just simplifying things. So we'll talk about that for a little bit while we're working through this problem. Okay, so sine of pi over 4, cosine pi over 3, since we have an exam coming up, I'll do a little bit of review here. If we want to find sine of pi over 4, I also at this point in the class, if you have these memorized and you can just fill them in, great. I assume some of you probably do. So pi over 4 is 45 degrees. We know our sides are 1, 1, and root 2. Sine is opposite over hypotenuse, so that means sine of pi over 4 is 1 over root 2. Now at this point, I don't need to rationalize my denominator. What I just need to make sure I do that is on my final answer. Okay, next step, cosine of pi over 3. So pi over 3 is 60. Let's draw a picture of that. We know our sides are 1, square root 3, and 2. So cosine of 60 is adjacent over hypotenuse, that's 1/2. Plus cosine of pi over 4, so adjacent over hypotenuse is 1 over root 2, times sine of pi over 3, so sine of pi over 3 is opposite over hypotenuse, that's root 3 over 2. Our next step here is to add our fractions. This should always work out on these problems that these two denominators match. So in the denominator here, I have 2 root 2. I'm adding something also with the denominator of 2 root 2. So we have 2 root 2. In the numerator here, I have 1 times 1, that's 1, plus 1 times root 3, that's root 3. Next step, anytime we get our answer, we should always make sure to reduce our fraction as much as possible, rationalize our denominator. Usually we should rationalize first if needed and then reduce. So here I need to get rid of this square root down here. So I need to multiply by root 2 over root 2. In the denominator, I have 2 times root 2 times root 2. So root 2 times root 2 is 2. 2 times 2 is 4. In the numerator, here I have 1 plus root 3 times root 2. I need to remember that this is being distributed to both of these terms. So 1 times square root 2 is square root 2. And then square root 3 times square root 2 is square root 6. Now, be very careful here. I see students all the time. You see a 2, you see a 6, you see a 4. It's very, very tempting to want to reduce all of these by a factor of 2. You cannot reduce something that's under a square root with something that's not under a square root, okay? So we cannot reduce this any further. Now, if you were taking a paper test, I would count this answer as correct with full credit. Typically, you'll see this simplified a little bit further. So anytime both of these terms are both radical expressions, they're both square roots, usually what we do is simplify the square root terms with the non-square root terms. So instead of leaving this as root 2 plus root 6 over 4, we would write this as 1/4 times root 2 plus root 6. The benefit of doing it this way is here's our radical expression, here's the non-radical expression, part under the square root, not part under the square root. If this didn't have a square root, we would leave it as one big fraction. But if everything's a square root, usually we separate that out. Okay, so on a paper quiz or a test, we would accept either answers as correct. On my math lab, if both of these terms are have a square root, you should pull out the non-square root term out in front. All right, any questions on this? Yes.
Okay, so for the degrees, right, would we put that in as our answer, or would we put it in the 1/4, like, square root 2 plus 6? Because I'm kind of confused about why we're doing that part.
You're confused, so you were asking about degrees. You're asking about up here?
Mm-hmm.
Okay, so if we had used degrees at this step instead of using pi over 4 and pi over 3, you could have written this as sine of 45 plus 60. And then what would happen is this all this way through, this would have been a 45 degrees. This would have been a 60 degrees. You would still have to find sine of 45, which is 1 over root 2. Cosine of 60 is still 1/2. Here you would write this as 45. Here you'd write this as 60. These numbers would still be the same.
Yeah, so if I'm
Yes. Yes. So whether you do this in radians or degrees at this first step, your final answer should be the same. Also at this step, I wrote mine as 1/√2. If you had written it as √2/2, if you had rationalized here, you should still get the same final answer as me. Any other questions? Okay, let's do some more. And of course, math is about practice, right? Once you get home and you practice this on your homework, you'll see how it works out and hopefully you'll feel a little bit more comfortable. Okay, next one. Let's find the value of cosine of 195 degrees. Okay, so this one's nice. It's already in degrees for us. Maybe you're more comfortable with that than radians. So what our goal is, we have a cosine, so we should have a cosine. We want to write 195 degrees as the sum or difference of angles that we know how to do by hand. Okay, so we want to write 195 as a sum or difference of angles that we know how to do by hand. Again, there's an infinite number of ways to do this. So think about this for a second. The angles we know how to do by hand are 30, 60, 90, multiples of 30, 60, 90, 45, 45, 90, multiples of 45, and then those quadrantal angles, right? Multiples of 90. Those are the two triangles on our quadrantal angles. Okay. So right off the bat here, because we see a 5, we know we need to use 45 somewhere, right? All the other angles, the 30, 60, 90 are the quadrantal angles with the 90. Those don't have a 5 in them. So because we see this 5, we know we're going to have to use the 45. There's an infinite number of ways to do this. You could have done, what did you guys pick? Anybody want to tell me what they picked? What plus what? Yep. That's what I used. Okay, so I used 135 degrees plus 60 degrees. That's exactly what I picked in that exact order. This is not the only way of doing it. You could do 45 plus 150. You could do something with a subtraction sign in there, right? So there's actually an infinite number of ways. Usually we want to pick the smallest numbers, and if something pops to you, great. So 135 is a multiple of 45. This is 45 times 3. And then 60, we know how to evaluate that by hand. Okay, so 2 angles we know how to evaluate by hand. This is going to be alpha, this is going to be beta. Now, if you had written these in the opposite order, 60 plus 135, and 60 was your alpha and 135 was your beta, you absolutely would still get the final answer the same. So it doesn't matter what order you do these in. Okay, so now what we want to do is we want to look at our formulas. So here's our formula. We have cosine of alpha plus beta. The plus is the top operator. This tells us this is equal to cosine alpha, cosine beta. The top operator is minus sine of alpha, sine of beta. So what I'm going to do is just plug everything into this formula. Where I have this alpha, I'm going to plug in 135 degrees. And where I have this beta, I'm going to plug in 60 degrees. And then from there, it's plug and chug and simplify. So I have cosine of alpha, which is 135, cosine of beta, which is 60, minus sine of alpha, which is 135, times sine of beta, which is 60. Okay, our next step, we know how to evaluate these. Remember, evaluate just means finding the value. We know how to come up with a number for these things, so we'll do those by hand. We'll plug those in, and then we'll simplify. Okay, so the first thing we need to evaluate is cosine of 135. So let's draw a picture of 135. So a 135, that's 45 times 3. Drop a perpendicular, forming a triangle. This angle is 45, so that means our sides are 1, 1, and √2. The other thing we want to remind ourselves, and the biggest mistake I see probably in this whole entire chapter, is students forgetting that when we're not in the first quadrant, we should always ask ourselves, should our answer be positive or negative? So let's remind ourselves we have all students take calculus. So let's just put an S here with a circle around it to remind ourselves that sine is positive and cosine and tangent are negative. Okay, so cosine of 135 is adjacent over hypotenuse. And cosine of 135, cosine in this second quadrant is negative. Okay, so make sure not to forget this negative. Next up, I want to multiply by cosine of 60. So let's draw 60 in again. And again, if you have these memorized, feel free to skip the pictures. So here's our 30, 60, 90. Our sides are 1, root 3, and 2. Okay, so cosine of 60 is adjacent over hypotenuse. That's 1/2. And in the first quadrant, everything is positive. Then we have minus sine of 135. So here's 135. Sine is opposite over hypotenuse. That's 1 over root 2. And in the second quadrant, sine is positive. Times sine of 60, here's our picture of 60. Sine is opposite over hypotenuse, and in the first quadrant, everything is positive. So that's root 3 over 2. This should always happen to you, that the denominators match because it's just the hypotenuse times the hypotenuse, so these should always match. So our denominator we have is 2 root 2. And in the numerator, I have -1 times 1, that's -1. And then I have -1 times root 3, that's minus root 3. The next step here is to rationalize the denominator. So I'm going to multiply by root 2 over root 2. In the denominator, I have 2 times 2, which is 4. In the numerator, I need to remember to distribute this to both of these terms. So I have minus root 2 minus root 6. On a paper quiz or a test, we would give you full credit for this answer. On the computer system and in general, if you ever have something with all square roots and not square roots, we would separate this out. So the more simplified way of writing this is by pulling out the minus from both of these two terms. Right? They both have a minus in common, a negative in common. And then we pull out this 1/4. And we write it as -1/4 times root 2. Oops, I'm saying it, but I wrote something else. Root 2 plus root 6. Let me move this chat box. Now, if you look at this answer, it looks a lot like our answer for the previous problem. And because all of these problems we're doing in this section are still based in just 2 triangles, you're going to see lots of root 2s, root 3s, root 6s, which is root 2 times root 3. Okay, so pretty much all section, we're going to see multiples of these things. Any questions on this one? Any questions? Okay, let's do another one. Okay, next one, let's find the value of tangent of 15 degrees. Tangent of 15 degrees. So the first thing we want to do is write this as the sum or difference of 2 angles that we know how to do by hand. Okay, so take a second and think about how you could write this as the sum or difference. Sure. Yeah, so somebody says 45 minus 30. That's what I used as well. What other pretty small angles could we have done this with? Yeah, I heard somebody whisper 60 minus 45. We could have written it as 60 minus 45. Okay, there's an infinite number of ways to do this. We could have done it as 150 minus 135. We could also do it as the sum of a negative angle and a positive angle. So we could have done -45 plus +30. Okay, so just realize that no matter what you pick to start out here, your work might look a little bit different from mine, but your final answer should still be the same. Okay. So what we notice here is we have tangent of 45 minus 30. I'm going to let this be my alpha and this be my beta. And then we're going to use the tangent formula. So let's pause for a second and take a look at the tangent formula because it is a little bit more complex than the first two. So our tangent formula here, the bottom operators go together. So here we have the minus in the bottom. So we're going to use the minus in the bottom and then the plus in the bottom. Okay, so again, the bottom operators all go together. So our formula tells us this is equal to tangent of alpha, which is 45 degrees, minus tangent of beta, which is 30 degrees, over 1, and then we're using the bottom operator. So in the denominator, the bottom operator is the plus. Tangent of alpha, which is 45 degrees, times tangent of beta, which is 30 degrees. Okay, so from this point, it's plug and chug, meaning we plug in tangent of 45, we plug in tangent of 30, and then we simplify. Okay, so I'll draw pictures of both of these for you. If you already have these memorized at this point in the class, feel free to just plug them on in and start working. So tangent of 45 degrees. Here's our picture for 45. We have SOHCAHTOA. So tangent's opposite over adjacent, so that means tangent's going to be 1. And in the first quadrant, everything is positive. The other one we'll need is 30. And we know our sides are 1 root 3 and 2, and tangent is opposite over adjacent, so that's 1 over root 3. Okay, so now filling this in, tangent of 45 is 1, minus tangent of 30 is 1 over root 3. At this point, if you had written root 3 over 3, that's fine. And in the bottom, I have 1 plus tangent of 45, which is 1, times tangent of 30, which is 1 over root 3. Okay, the complicated part is we need to simplify this. So what we don't like is fractions inside fractions. That's the first thing we don't like and the first thing we need to eliminate. The other thing we don't like is, of course, radicals in the denominator. So we need to address those two things. So the first thing I notice is this fraction inside my numerator has a root 3 in the denominator. This fraction inside my denominator has a root 3 in the denominator. So the first step I'm going to take is I'm going to multiply by root 3 over root 3, and that's going to get rid of the fractions inside the fractions. Okay, so this is kind of a shortcut. The other first step you could have taken if you wanted to was to actually do this subtraction and to actually do this addition. Then you'd have a fraction over fraction and you could switch to division and multiply. This little trick just makes things simpler right off the bat. Okay, so either method's just fine. So root 3, I need to distribute to both of these terms. So 1 times root 3 is root 3. And then here I have 1 over root 3 times root 3. These root 3s are going to cancel out, and it gives me a minus 1. In the denominator, again, I need to distribute to both of these terms. So 1 times root 3 is root 3. And then this is 1 over root 3 times root 3. The root 3 cancel, and we just get plus 1. Okay, the next thing we need to do is we need to eliminate this square root in our denominator. So anytime you have 2 terms in your denominator, and we want to get rid of the square root, we're going to multiply by the conjugate. So remember this from your previous math classes, the conjugate is the same numbers but with the opposite sign in the middle. So I need to multiply by root 3 minus 1. And if I do that in the denominator, I have to do that in the numerator as well. Well, we had some problems with that computer, so I'm continuing this problem. And you see here I'm on a different recording system. So we were working on computing tangent of 15 degrees, and we had gotten to this point where in order to get the square root out of our denominator, we were multiplying by the complex conjugate. So the next step here is to FOIL these both out. There are special rules for multiplying these out. If you know them, you're welcome to use them. I'll go ahead and FOIL them out. So FOIL stands for first, out, inner, last. So in the numerator here, root 3 times root 3 is 3. Outer, I get minus root 3. Inner, minus root 3. And last, plus 1. In the denominator, first, root 3 times root 3 is 3. Outer is minus root 3. Inner, plus root 3. And last, minus 1. Now, when we multiply by the conjugate, the whole reason why we do that is because these cancel out, and that should always happen. And then we get rid of the radical in our denominator. So I have 3 minus 1, that's 2. And in the numerator, I have 3 plus 1, that's 4. Minus root 3, that's minus 2 root 3. The last thing we need to do here is reduce our fraction or simplify. So to reduce this fraction here, I'm going to distribute this divided by 2 to both of these terms. So let's see, 4 divided by 2 is 2, and then minus 2 root 3 divided by 2 is just going to be minus root 3. Okay, so our final answer here is going to be 2 minus root 3. The next problem here, let's find the value of cosine of 70 times cosine of 20 minus sine of 70 times sine of 20. So we can actually use these formulas in both directions. So what we've done in the past few problems is we've had sine or cosine or tangent of an angle and we've split it up. I'm using the sum and difference formulas, but we can use this in reverse. So if we look at our list of formulas, this actually looks like our cosine sum formula. And what we're going to do is do this in reverse. So here's alpha, here's beta, here's alpha, here's beta. So our formula sheet tells us that this is equal to cosine of alpha plus beta. So 70 plus 20. So 70 plus 20 is, of course, 90. So we have cosine of 90 degrees. Remember, to find cosine of 90 degrees, the shortcut we can use, here's 90 degrees, is by looking at a point that's a distance of 1 away from the origin. The x-coordinate here is 0, the y-coordinate is 1. These go in alphabetical order, cosine, sine. So cosine of 90 degrees is just equal to 0. So what we did is we started with kind of a messy expression here, and we actually got that that was just equal to 0. Let's do one more. So let's find the value of tangent of 40 degrees minus tangent of 10 degrees over 1 plus tangent of 40 times tangent of 10. Okay, so again, we're able to use these sum and difference formulas in reverse. So in reverse, this of course looks like our sum and difference of tangent. This is going to be alpha, this is going to be beta, this is alpha, this is beta. We have to pay attention to the operators here. This is our formula for difference. So this is equal to tangent of alpha, which is 40, minus beta, which is 10. And the clue here, of course, is we only know how to do some of these angles by hand, so we should get something that's a multiple of 30, 60, or 90, or 45, 45, 90. Okay, so we get 40 minus 10 is, of course, 30. So tangent of 30. Our last step here would be to answer the question. So to find tangent of 30, let's draw that angle in. Drop a perpendicular to our x-axis. We know our sides are 1, root 3, and 2. We're asked for tangent, so we think SOHCAHTOA. Tangent is opposite over adjacent, so that is 1 over root 3. Rationalizing our denominators, we get that our final answer here is root 3 over 3. We have two other types of problems we'll see in this section. So next one, it's nothing different. It just kind of worded a little bit differently. So let's find the value. Given that tangent of alpha is equal to 5/12, and alpha is between pi and 3 pi over 2. And sine of beta is equal to -1/2, and beta is between pi and 3 pi over 2. We have two parts here. Part A, we're asked to find sine of alpha plus beta. And part B, we're asked to find tangent of alpha minus beta. So again, we're just using these sum and difference formulas. So the first thing I want to do is draw a picture of alpha and draw a picture of beta. So what do we know about alpha? We know alpha is between pi and 3 pi over 2. So here's pi, here's 3 pi over 2. So alpha is somewhere in here. Okay, so here's alpha. We are told the tangent of alpha is 5/12, so let's fill that in. We think SOHCAHTOA, tangent is opposite over adjacent. So using the Pythagorean theorem, we're recognizing this triangle. We get that the third side of the triangle is 13. Let me put a big alpha here to remind myself that this is my picture of alpha. Okay, let's draw beta. Beta also happens to be between pi and 3 pi over 2, so in the third quadrant. And here we're told that sine of beta is 1/2. So sine is opposite over hypotenuse. Using the Pythagorean theorem, we're recognizing this triangle. We get that the third side is √3. Okay, so sine of alpha plus beta, in order to answer this, we use our formula sheet. Our formula sheet says that this is equal to sine of alpha times cosine of beta plus cosine alpha times sine of beta. Next step is just to fill in the information. So if we look at our picture, sine of alpha, sine is opposite over hypotenuse, that's 5/13. And in the third quadrant, sine is negative. Don't forget to ask yourself, should my value be positive or negative? You can either use the shortcut, all students take calculus, or if you want to track these, right, this would be negative, this would be negative. So either way. Next up, let's fill in cosine of beta. So cosine of beta is adjacent over hypotenuse, and cosine in the third quadrant is negative, so don't forget that. And then we're going to add this to cosine of alpha. So cosine alpha is adjacent over hypotenuse, so that's -12/13. Cosine is negative in the third quadrant. Times sine of beta, sine is opposite over hypotenuse, and in the third quadrant, sine is negative. Last step here, let's multiply this out. So I get 5√3 plus 12 over 26. And that's our answer. Part B, we're asked to find tangent of alpha minus beta. So the first thing we're going to do is fill in our formula. Our formula tells us this is tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tangent of beta. So our next step is to fill in all of these values. So looking at our picture of alpha, tangent is opposite over adjacent, and tangent in the third quadrant is positive. So this is going to be 5/12 minus tangent of beta. So tangent's opposite over adjacent. So that's going to be 1 over √3. At this point, we have a lot of different ways to proceed. If you want, you can start adding these fractions together, adding these together. The shortcut that I like is to get rid of the fractions inside the fractions. So what I notice is that if I multiply both the numerator and denominator by 12√3, I will actually eliminate all of my fractions inside the fractions all in one swoop. So this is the shortcut I like. So I'm going to distribute this to both of these terms. So 5/12 excuse me, times 12√3 gives me 5√3. And then 1 over √3 times 12√3, the √3s we're going to cancel, leaves me with a -12. In the denominator, I have 12 root 3 times 1, so that's 12 root 3. And then here I have 5 over 12 root 3 times 12 root 3. The 12s cancel, the root 3's cancel, so I just get plus 5. Now the last thing we need to do is get rid of the radical inside our denominator, so I multiply by the conjugate. So the conjugate here is the same numbers, but with the opposite sign in the middle. And if I do that to the numerator or the denominator, I also have to do it to the numerator. So we're going to FOIL both of these out. So FOIL stands for first, out, inner, last. So first, I have 5 times 12, which is 60, and root 3 times root 3 is 3. Outer, minus 25 root 3. Inner, minus 144 root 3. And last, plus 60. In the denominator here, I have 12 times 12, which is 144, times root 3 is 3. Outer, inner, and last. So let's simplify and combine like terms. So in the numerator here, 60 times 3 is 180, plus 60, that gives me 240. And then here I have minus 25 minus 144 root 3, that's a total of minus 169 root 3. In the denominator, these middle terms should always cancel out. That's the benefit of multiplying by the conjugate. And we get 144 times 3 minus 25, which gives us 407, so that's our answer. The last thing we should do is evaluate on either of these answers if we can simplify or reduce them at all. And unfortunately here we couldn't really simplify, and here we can't simplify. But you should always ask yourself, can I simplify or reduce my fractions? I have one other type of problem where we might see in this section. And this problem is pretty fun. It asks us to find the value of cosine of inverse sine of 5/13 minus inverse tangent of 3/4. So remember here, anytime we see inverse sine, inverse cosine, or inverse tangent, those are referring to an angle. Okay, so this is the angle in between negative pi over 2 and positive pi over 2, whose sine is 5/13. This is the angle in between negative pi over 2 and positive pi over 2, whose tangent is 3/4. So these are just referring to angles, Okay, so I'll just call this whole thing angle alpha, and I'll call this whole thing angle beta. So now this problem is just asking us to find cosine of alpha minus beta. We know from our formula sheet that's just equal to cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. Okay, so now let's draw a picture of alpha. We'll draw a picture of beta, and then we'll fill in those values. So for alpha, alpha is inverse sine of 5/13. So remember, inverse sine is restricted to quadrant 1 or quadrant 4. The way we determine what quadrant the angle is in is based on this number being positive or negative. This is positive, so that means our angle is in the first quadrant. Sine is 5/13, so opposite over hypotenuse. Using the Pythagorean theorem or recognizing this triangle, we get that the third side is 12. Let's draw a picture for beta. So inverse tangents restricted to quadrant 1 and quadrant 4. Again, the way we determine what quadrant the angle is in is based on that number being positive or negative. We're looking for the angle whose tangent is positive, so that goes in the first quadrant. We think SOHCAHTOA, so tangent is opposite over adjacent. Using Pythagorean theorem or recognizing this, we get that the third side is 5. Next thing we do is we'll fill in these values. So we got that this is equal to cosine of alpha. So here's alpha. Cosine is 12 over 13. Times cosine of beta. Cosine's 4 over 5. Plus sine of alpha. So sine of alpha is opposite over hypotenuse. That's 5/13. Sine of beta, opposite over hypotenuse, that's 3/5. Okay, so 13 times 5 is 65. In the numerator, I have 12 times 4, that's 48. Plus 5 times 3 is 15. That gives me a total of 63 over 65. So a couple things to notice here. We know from our graph of cosine right from our graph that looks like this that we did in chapter 6. The maximum value cosine can hit is 1. The minimum value cosine can hit is -1, which means that regardless of how complicated this is inside here, our answer should still always be between -1 and 1 for any cosine problem. So 63 over 65, that's a little bit less than 1, so that is less than 1, so we're good. This is a really good self-check. If we messed up the math and say got 68 over 65, we know we've done something wrong. The other thing you should note here is because this is hypotenuse, 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 we should get common denominators for both of these, which we did, it was 65. So if you make those errors and things don't add up easily, you don't notice those common denominators, that's just kind of a good self-check. Let's do one more. So let's find the value of sine of inverse sine of 3/5 minus inverse cosine of -4/5. So again, anytime we see inverse sine, inverse cosine, inverse tangent, we should think that's just an angle. So I'm going to call this alpha and I'm going to call this beta. So now we're just asked to find sine of alpha minus beta. Our formula sheet tells us sine of alpha minus beta is equal to sine of alpha cosine beta minus cosine alpha sine of beta. The next thing we need to do is just fill these values in. So in order to fill those values in, let's draw pictures of alpha and beta. So alpha is inverse sine of 3/5. So because this is positive, that puts alpha in the first quadrant. Sine is opposite over hypotenuse. We get the third side of our triangle by Pythagorean theorem. We're recognizing that triangle. Okay, cosine. Oops, let me try this again. Beta. All right, inverse cosine is restricted to quadrant 1 and quadrant 2. The way we determine what quadrant our angle is in is based on this value being positive or negative. Here we're looking for an angle whose cosine is negative. So if cosine is negative, that puts it in the second quadrant. So cosine is adjacent over hypotenuse, and this third side by Pythagorean theorem, we're recognizing this triangle as a 3. Next up, let's fill in these values. So sine of alpha is opposite over hypotenuse, that's 3/5. In the first quadrant, everything's positive. Cosine of beta is adjacent over hypotenuse. And in the second quadrant, remember all students take calculus, cosine is negative, don't forget that. Minus cosine of alpha, so here's alpha, cosine's adjacent over hypotenuse, so that's 4/5, and in the first quadrant, everything's positive, times sine of beta, here's beta, sine is opposite over hypotenuse, and in the second quadrant, sine is positive. Next step here, we have common denominator 5 times 5, which is 25. Now I have 3 times -4, which is -12, minus 4 times 3, which is 12. So a total of -24 over 25. Okay, a couple things to notice. So we're asked to find sine of this complicated thing. We know what our sine graph looks like, right? It looks something like this. So as with cosine, the max value that sine can hit is 1 and the min is -1. So we should check that regardless of how complicated this thing is in the middle, our final answer should be between 1 and -1. And it is, right? -24 over 25 is a little bit bigger than -1, so that looks good. Again, your denominator should match here, so it should be easy to do this addition.